Okay, let's move to the question 7. So question 7, the following data is given. So mass, radius, surface temperature, core temperature, and core density of the sun, right? They said when it enters the main sequence, and question A1 say that state and explain which of above features makes nuclear fusion in the sun possible. Okay, so if you think about the nuclear fusion's conditions, so we need really high core temperature, and also we need really high pressure, right? So we need to achieve that two conditions. So we can say actually to overcome the electrostatic repulsion, they requires very high, we can say surface over core temperature, more likely to have the core temperature, right? And high pressure as well. So in the data, we can see the core temperature is 1.5 times 10 to the 7 Kelvin. And also for the pressure, we have, inside of the pressure, we have the core density, which is really high, 1.6 times 10 to the 5 kilograms per meter cube. That accomplishes the high temperature and the high density, which goes to high pressures, right? So the core temperature is high enough, and we have really high core density. That means that we have the high pressure. Okay, so moving to the question A2, they say outline how the sun maintains its equilibrium state. So they want to know what's the conditions for the equilibrium state. So when the equilibrium state, they have two equilibrium forces towards each other, right? So if you think about the sun, because of they have the fusions inside of the sun, they have something called the radiation pressure going outward from the sun inside to the outside, right? So we have outward radiation pressure. And we need some other forces that comes inwards, right? So that they have balanced force each other. So that means that they have the equilibrium state. So what do we have for the sun? We have the inward gravitational force, right? So that equals to inward gravitational force. Okay, so that's the answer for the question A2. All right, moving to the question B. They said the following the sequence of nuclear fusion reactions takes place in the sun, and stage 1, 2, and 3 are given, right? And they have the mass data is given. And they said estimate the energy release in stage 1 of those reactions. So we only going to consider the stage 1 in this case. And if we want to know what is energy release from this process, we need to compare the right-hand side and left-hand side, right? So we need to collect all the energy from the left-hand side, and we need to compare all the energy collected in right-hand side. So let's think about the left-hand side first. In the left-hand side, we have 2, 1, 1 hydrogen, right? So we have hydrogen of 2. In this case, the data for the mass is given, so we gotta use the mass. So they said one mass of the one hydrogen is 1.007276 U, but we have 2 of them. So that equals to 2.014552 U. Okay, and that's it for the left-hand side, right? And let's go into the right-hand side. The right-hand side, the data for the deuterium, which is 2, 1 hydrogens, is given, and we have electron and neutrinos for them. However, if you think about the electron mass, but that's actually not electron, that's a positron. Anyway, so mass of the electron and positron are the same. So anyway, the electron's mass, if you think about, and the neutrinos mass, it's relatively too small compared to the deuterium. So in this case, you don't have to consider the mass of electron and mass of neutrino. Okay, you can only consider the mass of deuterium. So that mass is given as 2, 1 deuterium is equals to 2.013550 U. Okay, we have 2 total masses, left-hand side and right-hand side. So now we have to compare the 2 masses, okay? So we need to calculate what's the mass defect in this case. So mass defect is just simply, you just like subtract between them, right? So that's 2.014552 minus 2.013550 U. which is equals to 4.53 times 10 to the negative 4 U, right? Okay, so now we have to convert U to the energy E, right? So we need to use the equation E equals to mc squared in this case. So E equals to mass, which is 4.53 times 10 to the negative 4 U times C squared. However, if you can actually do like converting U to mass in kilogram. However, that makes complicating this question. So I think the easiest way is 4.53 times 10 to the negative 4. And if you go to the formula booklet, you will find the number for the U, which is 931.5 mega eV times C to the negative 2. You will find that number instead of the U. Now we have C squared, so we have to multiply by C squared as well. But if you look closely, the C negative 2 and C squared can be cancelled out. So you don't have to think about the C squared part in this case. You don't have to convert into kilogram things, okay? So if you calculate that one, you will simply find that 0.42 mega eV. So in this question, they don't have any thing to say. We need to put the answer as the joules or mega eV, so you can actually leave it like that, okay? So the answer should be 0.42 mega eV. Getting to the question 7c, they said the sun will leave the main sequence when it has converted 10% of its hydrogen mass into the helium, right? And they said the total energy released in this reaction in B is 4.3 times 10 to the negative 12 joules. The current luminosity of the sun is 3.8 times 10 to the 26 watts. So when the sun enters the main sequence, its hydrogen mass has 1.5 times 10 to the 30 kilograms, okay? So I think this question is quite hard. So I think the student might find it really hard. I think it spends a lot of time if you get the wrong directions. But this is how I solve. Okay, so firstly, I will maybe draw the diagram, something like this. So we have the sun here. But if you read it carefully, they said 10% of the hydrogen mass into the helium. So if you go into these stages things, I think they talking about the stage 2, right? Because the hydrogen goes to helium. So I think they are talking about the stage 2. So the hydrogen of the stage 2 goes to the helium in these sections. So they said, initially they said they had 1.5 times 10 to the 30 kilograms of the hydrogen, and they said only 10% of them gets converted into the helium, right? So I can say only 10%, so I can multiply times 0.1, so that's gonna be 0.15 times 10 to the 13 kilogram has converted into the helium. But during the section of stage 2, think about how many hydrogen has used in this stage. For example, if it goes there, I can see 1, 2, and 3, and 4 protons. You can say hydrogen and proton at the same time in this question. So in total, 4 protons or hydrogens are used in this stage. So I can say in stage 2, the energy released per hydrogen per hydrogen mass can be equals to, they said the total energy used in this process is 4.3 times 10 to the negative 12, but I need to divide into the full hydrogen because full hydrogen are used, right? So 1 hydrogen mass was given in the previous questions, which is this, but we had 4 protons or 4 hydrogens are used in total, so I'll say 4. If you calculate that one, we'll have, so obviously in this section you have to convert it U into the kilogram in this process. So you have 6.425 times 10 to the 14 joules, okay? So that's the energy released per hydrogen. So now I want to calculate what's the total energy from this hydrogen, okay? So in total, we have this much of the hydrogen converted into the helium, right? So we have 0.15 times 10 to the 13 kilogram. However, I said we calculated the energy released per hydrogen per mass, right? So that's 6.425 times 10 to the 14 joules. So the total energy released should be 9.64 times 10 to the 43 joules. So that's the total energy. But in the question C1, they say show that the sun will stay on the main sequence for about 8 times 10 to the 9 years. Okay, we need to calculate the time. But one more data is given, which is they said the luminosity of the sun is equals to 3.8 times 10 to the 26 watts, right? If you think about the luminosity, it's the same as power, right? But the power is equals to energy over time. So using this luminosity, we can actually calculate the time in these sections. Okay, So we can say the time is spent, T is equals to, if you just swap that E over L, you can actually say. Okay, so that is equals to the total energy we just calculated, which is 9.64 times 10 to the 43 divided by the luminosity of the sun is given as 3.8 times 10 to the 26 watt. So that gives us the time. Okay, if you calculate that one, they have 2.537 times 10 to the 17 seconds. So now you have to convert it into the years, right? So if you want to calculate in the years, it's just unit conversion, right? So divided by, so 1 year goes 365 days, and 1 day goes 24 hours, and 1 hour goes 60 minutes, and 1 minute goes to 60 seconds. So you have to divide into that numbers. Then it will gives 8.039 times 10 to the 9 years. So that's about 8 times 10 to the 9 years. Right. In question C2 said, state one assumptions that was made in getting the answer to C1. So this answer is actually not the exact answers, right? So the sun will not actually remains the same luminosity as they get smaller, right? When they lose their mass, the luminosity value will be decreased. Okay. So I think the assumption that we can make for the question 2i was that the luminosity value should be constant over time, but actually it is not, right? So the luminosity is constant over time. Okay, so moving to the question C3, they said estimate the total mass lost by the sun in this time. Okay, so if you think about the mass lost, the only equation I can think about is E equals mc squared, right? So E is just the total energy released from the sun, right? So if you want to calculate the total energy released from the sun, is actually it's a luminosity times time t. You can say the luminosity of the sun was 3.8 times 10 to the 26, and the time it took was we just calculated, right? 2.537 times 10 to the 17, which is equals to 9.5935 times 10 to the 43 joules. But I think this value is the same as total energy we calculate in question C1, right? So I don't see any difference between them. So you can actually use the value we just calculated, which is 9.64 times 10 to the 43. But I stick with these numbers for now. Okay, using this number, we can say E equals mc squared using that one. So I can say 9.5935 times 10 to the 43 is equals to mc squared, right? So m is the mass defect, which in this case, mass lost by the suns during this time. And we just divide it by the c squared. So m is equals to this number divided by the c squared, which is 3 times 10 to the 8, that squared. So that should be equals to 1.067 times 10 to the 27 kilogram. Okay. Right. Lastly, question D said the surface temperature of the sun is 5,800 Kelvin. Determine the peak wavelengths in the sun spectrum. So if you see the word peak wavelength or the maximum wavelengths, you will instantly think about the Winslow. Okay. So Winslow said that the peak or the maximum wavelength times temperature in Kelvin is equals to 2.9 times 10 to the negative 3. So the temperature of the sun is given as 5,800 Kelvin. So you just like divide that number into this number, then you will know the answer. So that is equals to about 4.99 times 10 to the negative 7 meters. So you can say that is about 500 nanometer. Okay, let's get into the question 7e. So you'll see this picture and they said the sun rotates about its axis P is the point on the sun's equator. So when I see actually these pictures, I thought it's gonna be the question about 8.4, which is a rigid body dynamic because it's rotating, right? However, if you read it carefully, it's actually not about that, right? Because they have the two wavelengths are given. The one wavelength said 656.2797 nanometers, and they said the second, which is a changed wavelength, is 656.2753 nanometers, right? So when we have the two different wavelengths and they are changed, right? Because one wavelength changed to the other, but that effect is something called Duffel effect, right? So it's actually about the Duffel effect. The question E1 said explain the observations, right? So in a laboratory, they said the wavelength of the initial is equals to 656.2797 nanometer, and then the second wavelength, outside wavelength shifted, is equals to 656.27 0.2753 nanometers. So they have the wavelength changes, right? So the wavelength decreased, which means that the same meaning the frequency increased, right? So when frequencies changes, when there is a relative motions between them, that causes the Doppler effect, right? So this observation is about the Doppler effect. Okay, and the question E2 says that the calculate the period of revolution of the sun. So we need the time taken for the one complete revolutions. But if you think about like what's the equation we should use in the Doppler effect, and the information for the wavelengths are given. So that's actually delta lambda over lambda is equals to, you see, V over C, right? But before you actually substitute the number, let's think about like how we're going to actually solve like this equation to calculate the period, right? So if you actually know what's the velocity for them, you can actually know what's the angular speed for them, because using the V equals to omega times R, okay? And the radius in these questions is givens, right? Because they have the sun's radius, okay? So the sun's radius data is given in this section here, right? So sun's radius, this one, 7 times 10 to the 8 meters, right? Right, so then we can actually calculate the angular speed for this using this equation. And using angular speed, you have omega equals to 2 pi over period, right? So using this one, we can finally get the period here. Right, so let's substitute the numbers here. So delta lambda is a change in frequency, so that's the difference in between these numbers, which is 656.2797 minus 656.2753. So, and don't forget about the nanometers, and divided by the lambda. The lambda in a denominator, it should be the original, so from the lab, okay? So from the lab and from the earth, right? So it should be like 656.2797 nanometer, okay? So the nanometer cancels out, and if you use the calculator, you will see the number 7.604 times 10 to the negative 6, and that is equals to V over C. Then if you calculate the V, so C should be shifted to the left-hand side, and C is 3 times 10 to the 10 to the 8, right? So then you will see the velocity value is equals to 2011, right? And then that is equals to omega times R. So the omega times radius R. However, the radius R value was given in the first data, right? So that's 7 times 10 to the 8. So using that value, you can say omega equals to this value. And I just leave it as something like this for now. So now we have to calculate what's the period. So T is equals to 2 pi over omega, right? So that is equals to 2 pi over 2011 divided by 7 times 10 to the 8. So if you calculate that one, you will see the number 2.19 times 10 to the 6th second. Okay, so you can actually leave it like that, but if you want to change into the other units, you can say actually it's about the 25 days. Okay, let's move on to the last question. Question 8. A1 say that show that in time delta t, the mass of the spacecraft will increase by the amount rho SV delta t. So if you want to solve this question, I think you need to have some sense for that, because the mass, they want the mass, right? And the density data is given. So I think things that we can use is the density rho is equals to mass over volume, right? And the mass is equals to rho times V. However, the volume is not actually given in this data. We have to change it into something, right? So rho times, instead of the volume, we have the surface area, in this case S, times the length it travels, right? So I would say just L in this case. However, the length it travels, we can actually convert it into, because we have the velocity. So the distance it travels is actually S times the V times change in time, right? So that actually gives mass m equals to rho SV delta t. That's something the question A1 wants, right? So this is how we solve. And moving to the question A2, they said deduce that the spacecraft will experience a drag force rho SV squared opposite to its velocity. So we want the drag force. But if you think about the drag force, you will instantly think about the Stokes law, which is Fd equals to 6 pi eta RV. However, we don't have anything about the eta, which is the viscosity. So we cannot actually use this equation in this question. So if you think about the drag force, you can actually have to calculate the force for that. So F equals ma. But if you think about the acceleration acceleration a is actually delta v over delta t, right? So I can actually set up this equation, which is equals to actually change in momentum over change in time. It's the same things. But now I can actually use, instead of mass m, I can use this rho s v delta t times delta v over delta t. And as you can see, delta t cancels out, and it'll have rho s v times delta v, which is equals to actually rho s v squared. Okay, so that's the drag force they wanted in question 2. Okay, moving to the question 8, B1, they said the satellite of the mass m is in circular orbit of the radius r around the Earth, and they show that the total energy of the satellite is given as E equals to negative gmm over 2r, right? So in this question, we need to show what's the total energy. So the total energy is equals to the gravitational potential energy plus the kinetic energy, right? But think about that's in a circular orbit. So the gravitational potential energy is always negative gmm over the radius r, right? However, if you think about the kinetic energy, it's half mv squared. However, if you think about this v is orbital speed, right? So you will find it formula booklet that is equals to root gm over r. So if you substitute that numbers, gmm over r plus half times mass times v squared, so that's gm over r. So that is actually equals to gmm over 2r, right? So if you do like negative gmm over r plus gmm over 2r, that is equals to negative gmm over 2r. So this is how we show the total energy. So moving to the question B2, they said the satellite experienced a drag force during the atmosphere of the Earth. With the reference to the answer in A and B1, state and explained the likely fate of this satellite. Okay, so we know the question A, so they'll have some drag force on it with this amount, right? So if you think about it, it's rho s v squared. So if the v squared is getting bigger, they have the more drag force, right? So we can say the greater the speed, they have more drag force. And also the drag force, it leads the energy loss, right? And we can say because the energy, the total energy is decreased, right? The total energy decreases, which means that if the total energy decreases, the ET decreases. That is equals to negative gmm over 2r, right? But normally, if we don't have negative sign in front of that, if the total energy decreases, we can actually say the radius should increase, right? However, because they have the negative sign in front of that, we can say they should decrease, okay? Because it's a negative value, okay? So we can say when the total energy decreases, the radius is also decreases, which means that if you experience the drag force constantly, it will just like keep decreasing the radius, right? So the satellites like gradually spiral inside, and then it will just collide with the ground, okay? So that's the fate. Okay, moving to the next question. The one diagrams is given, and they said some data also is given. They said for the 30 days period indicates in the period, the loss of total energy of the ISS is 4.5 times 10 to the 9 joules, right? And the question A1 said that calculate the average rate at which the energy of ISS is being dissipated. Okay, so we want the average energy dissipated, the rate at which the average energy dissipated, okay? So I mentioned in the early questions, they said if you calculate the rate of something or the rate at which something, in this case, energy dissipated is always equals the rate at which, or the rate of something is always divided by change in time, right? And the energy dissipated in this case is just energy dissipated in this case. something like that. You always add this, if you have that word, just add equation, something like that. Okay, so that is actually equals to power. Okay, so that equals to the energy dissipated is given, so 4.5 times 10 to the 9 joules divided by the time it took. They said it's 30 days period. Okay, so 30 days, 1 day is 24 hours. 24 hours is equals to 3,600 seconds. So if you calculate that one, you'll have 1,736.11 watts. So that's about 1.7 times 10 to the 3 watts. Okay, moving to the next question. They said show using the average height during the 30 days period, the speed of the ISS is about 8 times 10 to the 3 meters per second, right? So if they want the speed of ISS, the ISS is the satellite, right? And they circle the orbit. So they should have the orbital speed equations. So V orbital is equals to root gm over r. So if you think about the radius, these sections, and think about the satellite is in this height, and we actually need to calculate the radius of the Earth and the plus average height of the satellite. That gives the total radius that you should use, right? So if you think about the radius first, that is equals to the radius for the Earth plus the average height. So if you actually see the average height for that, we have during the 30 period from the 0 days and to the 30 days, we have like changes in height from this number, which is 418.7, right? And it end with this height, which is here, is actually, you can say 416.2 meters, right? So we need to calculate what's average between them. It's pretty easy, right? So that's the midpoint between them. So that is equals to 418 plus 7 plus 416 plus 2 over 2, right? So that's the average height. Plus the radius is actually, and don't forget that's kilometer, right? Kilometer. Plus the radius given as 6.38 times 10 to the 6 in the data. So that should be equals to 6.79745 times 10 to the 6 meters, okay? So that's the radius that we should use with these numbers. So that is equals to root. So G value is 6.67 times 10 to the negative 11 times the mass of the Earth is given in a formula, in a data. So 5.98 times 10 to the 24 kilograms divided by the radius that we just calculated, 6.79745 times 10 to the 6. So that should be equals to 7,660 meters per second. So that is about 8 times 10 to the 3 meters per second. Right, moving to the next question, they said estimate the increase in temperature of ISS assuming all the lost energy went into the thermal energy of the ISS. Take the specific heat capacity of the ISS is to be 500, right? Okay, so they have the word specific heat capacity. Every time when you have the word specific heat capacity, the only equation that we can use is Q equals to MC delta T. Okay, so be sensitive to a specific keyword, okay, the specific heat capacity, then you should instantly think about this equation. So we want to calculate the increase in temperature, which is this one. So we want delta T, that is equals to Q over MC. But that is about the ISS, right? It's not about the Earth, so don't use the Earth data in these questions. So Q in this case, the thermal energy lost was given in this questions. They said the energy loss was 4.5 times 10 to the 9. So that's 4.5 times 10 to the 9. That's the total energy lost divided by the mass of the ISS, which is 4.2 times 10 to the 5 kilogram times specific heat capacity, which is 500. So if you calculate that one, that's 21.43 Kelvin. So about 21 Kelvin is increased. Okay. Right. The next question. Question 4, they said estimate using the answer to CI and C2 the average drag force acted on the ISS. Okay, they want the average drag force and they want us to use the data for CI and C1 and C2, right? And if you think about the C1, from the C1, the value we calculated is power, P equals to 1,736 watt. And from the 2, the data we calculated was the velocity is equals to 7,660 meters per second. And they now want to calculate what is the average drag force, okay? So the drag force if you use that data, it's pretty easy, right? Because we have the power P equals to force times velocity. And if you think about it, it makes sense because the power P is the one you calculate in one question I said that that's energy dissipated. Okay, so that's energy lost, and this force is actually the drag force they said they want to calculate. So that makes sense. So okay, so we just substitute the numbers here. F equals to P over V. So that's this, and the number is about 0.266 Newton. Oh, that's actually 0.2266 Newton. Okay. Right, so let's move on to the last question, which is question 8D. They said at the end of the 30 days period, the rockets are fired to bring the ISS back to its initial height. The energy density of the liquid hydrogen rocket fuel is 8.5 times 10 to the 3 megajoules per meter cube. They said estimate the volume of fuel needed. Okay, so the density, energy density is given, but if you think about the energy density, is energy required divided by the volume, right? So if you want to calculate the volume, V equals to energy required, the energy needed divided by energy density. So what is energy required, energy needed for the rockets to bring the ISS back to its initial height? You think about the ISS actually lost from initial height to the 30 days period was 4.5 times 10 to the 9, right? That was the energy being lost. Okay, so 4.5 times 10 to the 9 divided by the energy density in this case is 8.5 times 10 to the 3 mega, so should have 10 to the 6. Okay, so that is equals to 0.5294 meter cube. So that is about 0.53 meter cube.